In this section, we obtain two formulas relating theta of x and phi of x, theta of x and phi of x. These formulas will be used to show that the prime number theorem is equivalent to the limit x tends to infinity, theta of x divided by x equal to 1. In similar fashion, as we consider phi of x as a step function, theta of x can be considered as a step function as well. That is, if we consider the graph of step function, uh, here I'll take here x this way and phi of x this way. So if we draw the graph of phi of x up to the prime number 2, we have 0 because there is no prime less than 2. Then at the point 2 we have 1 prime, so the value of 2 is 1. The value of 2 is 1, and at the point 2 onwards we have up to 3, the value is 1. Okay, so the value of 3 is nothing but 2 because at the prime number 3 we can get 2 primes, 2 and 3. At the point 3 we have the images at here, and from 3 onwards up to this 5 we have the value 2 up to this point. At the point 5 we have values 3 because there are 3 primes, 2, 3, 5, and at this point we have up to this point we have the values 2. So this shows that this phi of x can be considered as a step function. Similarly, in the similar fashion, you can consider the graph of theta of x. Here this jump is it's every stage the jump is 1. Here we have jump is 1 again. Now we consider the graph of theta of x. Theta of x is the definition of theta of x is, we know that the definition of theta of x is equal to summation p less than or equal to x log p. Okay, so that is at x equal to, I take x here and theta of x here. If x equal to 1, we have the value is if x equal to 1, you have there is no prime, so we take it as 0, and the value is at the point 2 we have 1 prime, that is 2, so that is log 2. At the point 3, in between this the value is 0, in between these two the value is log 2 itself. So at the point 3 we have log 2 plus log 3. At the point 4 we have the same value. At the point 4 we have same log 2 plus log 3, and at the point 5 we have log 2 plus log 3 plus log 5. So if you draw the graph of this file, take x along this way and y of x along theta of x along this way. Up to this point, up to the prime number 2, we have value 0. As in the case of phi of x, we have this, and at the point 2, the value is log 2. Point 2, the value is log 2. Log 2 is always less than 1, so we have some value over here. That is up to the point 3, we have log 2. Log 2 is some value less than 1. So at this point, we have up to this 3, we have this step function. And at the point 3, we have log 2 plus, suppose this is log 2 plus log 3. Log 3 is greater than 1, so we have more than 1 unit here. So up to the point 5. Okay. Then 5 onwards, we have up to the point 7, we have log 2 plus log 3 plus log 5. That is again like this. Okay. Point. Okay. So this shows that the jump here is up to this point, the jump is log 2, and up to this, we have the jump log 3, and this will be the jump log 5. So these two are step functions, but both have the different jumps. Okay, if you consider pi of x, then we have jump in each state the jump is 1, and in case of theta of x the jump is not 1. That varies. That is like log 2, log 3, log 5, etc. These sums can be expressed as integrals using the following theorem, Abel's identity. That theorem 4.2. This is Abel's identity. The theorem states that for any arithmetical function a of n, let capital A of x is the partial sum of that. Summation n less than or equal to x a of n, where this a of x is also defined for x less than 1, value 0 if x is less than 1, and assume that f of x has a continuous derivative on the interval y comma x, where 0 less than y less than x. Then we have the statement or equation, that's what we called Abel's identity. Summation y less than n less than or equal to x a of n f of n. So this is a discrete sum that is related to the continuous sum, the integral. A of x f of x minus a of y f of y minus integral y to x a of t f dash t dt. So this is what we call Abel's identity. Proof. For this we let k equal to integral part of x and m is equal to the integral part of y. Then we have a of x is same as a of k, and a of m is same as a of y. So we have let this is 0. Since this y is 0 is less than y is less than x, we have y here, and x can be somewhere over here. Then integral part of y is defined as k, so this is m, and integral part of x is defined as k, so that is k here. So we will then we know that there is no integer between, since this is the integral part of y and this is the integral part of x, there is no integer between these two. So a of k is same as capital A of x, capital A of m is also same as capital A of y. This is our present situation. Then LHS becomes summation y less than n less than or equal to x a of n f of n. This is equal to the first integer after this y is m plus 1 here. So this is the summation n is equal to m plus 1 to the last integer is the integer part of x, and that is k. Then we replace this a of n as capital A of n minus capital A of n minus 1. So that is a of n minus a of n minus 1 times f of n. Then by distributing this sum, we can get summation n equal to m plus 1 to k a of n times f of n. Next time will be minus summation n equal to m plus 1 to k a of n minus 1 times f of n. And we write this is equal to summation n is equal to m plus 1 to k a of n f of n minus summation n equal to m to k minus 1 a of n f of n plus 1. So this gives the same sum that we have written here, because the sum contains the terms a of m f of m plus 1 into a of m plus 1 f of m plus 2 plus etc. a of k minus 1 f of k. So this will give the same sum. So you can write this as, so this is equal to summation n is equal to m plus 1 to k minus 1 a of n f of n. I remove one term from the sum, the term corresponding to n is equal to k. So I add that term as a of k f of k, and we consider the next sum. I'll write the next sum as minus summation n equal to m plus 1 to k minus 1 a of n f of n plus 1. I have removed the term corresponds to n is equal to m, so that I remove from this sum. So that is a minus of a of m f of m plus 1. This is the term that we have not included in this sum. So this can be grouped because the summation variations are same. So this becomes equal to summation n is equal to m plus 1 to k minus 1. We can group these two, so that will that a of n can be taken out from those two terms, times we have f of n minus f of n plus 1. The intention is to do this, incorporate the integral to this sum. So the remaining term will be a of k f of k minus a of m f of n plus 1. and this can be replaced by integral of something. So this is the integral of f dash from n plus 1 to n, so that can be written as minus integral of n to n plus 1 f dash of t dt. So this is equal to summation n equal to m plus 1 to k minus 1 a of n. This can be written as minus of integral n to n plus 1 f dash t dt, minus the same terms a of k, f of k, a of m, f of m plus 1. This is equal to, if you consider this interval n to n plus 1, this a of n will give, or a of t is always equal to a of n. So if we can take this a of n inside, because this is the variable of here the variable of integration is t, so that becomes minus of summation n equal to m plus 1 to k minus 1. I'll write this as integral minus integral n to n plus 1 a of t f dash t dt, because the value of a of t is always a of n for the interval n less than or equal to t less than n plus 1. So this, the remaining term will be the same, a of k, f of k, minus a of m, and this is plus, we have plus sign here, we have plus, and here we have a of m, f of m plus 1. Now we sum these integrals, then you will get this is equal to minus of integral. The first value is m plus 1, so this integral is from m plus 1 to the last value will be k minus 1, so k minus 1 plus 1, that is k. So this integral is from m plus 1 to k a of t f dash t dt plus a of k f of k minus a of m f of m plus 1. But we know that this a of k is same as a of x, and a of m is same as a of y. So you can replace these two quantities by a of x into a of k, a of x by a of k, and a of m by a of y. If you consider this integral is from m plus 1 to k. That means this integral is from uh, this point from this point. So in order to get the integral from y to x, we need to consider two more integrals, or we need to incorporate two more integrals. The first integral is y to m plus 1, and the next integral is k to x. So we need to incorporate these integrals to this integral, then only we can directly convert that discrete sum as a integral or continuous sum. For that, consider the integral. First, you consider integral k to x uh, a of t f dash t dt. In this interval k to x, this a of t is always a of k. So this is a of k into, and this the remaining integral will be integral of f dash t from k to x. So this is f of x minus f of k. So the sum is a of k f of x minus a of k f of k. Now you can replace this a of k f of k using this equation in this equation. So that we can get integral from k to x inside this formula. So similarly, we consider another integral from y to m plus 1, the same quantity I of t f dash t dt, and that will give almost the same formula like this, because this a of t, the value of a of t is always a of y. We can write this as a of m into the remaining will be f of m plus 1 minus a of m into f of y. So we can replace these two quantities, f of a of m into f of m plus 1 and a of k into f of k, in this equation. So this becomes minus integral m plus 1 to k a of t f dash t dt. How we replace this a of k into f of k? A of k into f of k is this minus this one. Okay, so we write it as plus a of k into f of x. A of k is same as a of x, so you will write this as a of x into f of x minus of this integral minus k to x a of t f dash t dt. Then we replace this minus of a of m f of m plus 1. So minus of that will be, we can transpose this a of m f of m plus 1 to the left, and we can transpose this integral to the right. So that will be minus of integral y to m plus 1 a of t f dash t dt minus the remaining term a of m into f of y. A of m into f of y same as a of y into f of y minus a of y into f of y. Then this is equal to, if we combine these three integrals, you will get this the integral from k to x, and this from this you can write this one y to m plus 1, this is m plus 1 to k, and this is k to x. So that will be minus of integral y to x a of t f dash t dt minus, or I'll write this is plus a of x f of x f of x minus a of y f of y. So this is what we call the Abel's identity. So next we can find an application of this Abel's identity that gives the relation between theta of x and pi of x.